In this lecture, we are going to discuss the situation when the transversality condition fails. The outline for the lecture is as follows. First, we discuss failure of transversality condition and its consequences, what can be expected in when there is a failure of transversality condition. Then we look at illustrative examples where transversality condition fails. There are two examples, they illustrate the two possibilities that we can conclude in the case when transversality condition fails. And then we look back at the three examples which were motivating examples which were dealt in lecture 2.1. It was Cauchy problem, 3 Cauchy problems for the same differential equation, same PDE, wherein we saw one has exactly one solution, other Cauchy problem has infinitely many solutions, and the third one had no solutions. So, we are going to analyze those examples in the light of this failure of transversality condition. In the proof of existence and uniqueness theorem, the transversality condition played an important role in both existence and uniqueness assertions in proving both of them. So, therefore, it is natural to ask what happens if transversality condition is not satisfied. We expect that the Cauchy problem may not have a solution, that is existence is violated, no existence. Second aspect is uniqueness is violated, that means it has more than one solution, or it may still have one and only one solution. Are you surprised? No need to surprise, because the theorem, if you remember, the assumption of transversality condition was only a sufficient condition. Under that condition we have proved existence and uniqueness. So, if the sufficient condition is not satisfied, still we may have existence of a unique solution. I would like to recall your attention to one of the very important ordinary differential equation problem. Let me write that equation: y dash equal to y sin 1 by y, obviously when y is not 0, and 0 when y equal to 0, that is to be expected, and then y of 0 equal to 0. So, this initial value problem, okay, the theorem that we have is Pinot's theorem and Cauchy-Lipschitz-Picard's theorem. When we apply Pinot's theorem, yes, the right hand side is a continuous function, therefore, there is no problem, it has a solution. Now, the right hand side is not a Lipschitz function, that you can check it, because it is not Lipschitz, Cauchy-Lipschitz-Picard theorem cannot be applied and uniqueness be concluded, we cannot do that. So, therefore, we can expect that maybe there is more than one solution. In ODEs, it so happens that when you have two different solutions for the same initial problem, there are infinitely many solutions actually. So, that is the only possibility. So, you have no solution or one solution or infinitely many solutions, these are the only possibilities for ODEs. Now, here it so happens this problem, the right hand side is not a Lipschitz function, this is not locally Lipschitz. If you call this as f of y, there is no y x dependence, so I do not write. So, this is locally not locally Lipschitz. It is not locally Lipschitz. Therefore, we cannot apply the theorem, but still it so happens this has a unique solution. So, that I leave it for you. If you have not come across this question already, please look at it and show that solution is unique. So, violation of sufficient conditions means nothing, no conclusions can be drawn. That is why we may still have one and only one solution, it can happen. Okay. So, if the transversality condition is not satisfied and a solution to the Cauchy problem is expected, that means the Cauchy problem has a solution, then something should happen. The datum curve must necessarily have a characteristic direction at each of its points, which means that it is a characteristic curve. Now, we have a result lemma 1, it is a very simple result. Let z equal to ux y be an integral surface corresponding to the Cauchy problem for quasi-linear equation QL containing a part of the datum curve which is called gamma dash, that corresponds to, you see, gamma corresponds to S belongs to I, gamma dash corresponds to S belongs to I dash, where I dash is a subinterval. Now take a point on gamma dash and denote J0S is precisely the determinant which comes in transversality condition. AB here, F dash G dash. AB is the tangential direction for the base characteristic curve at base characteristic curve passing through the point FSGS, but because it is quasi-linear it is tied up with the value HS also. F prime G prime is the tangential direction to the base characteristic curve, not base characteristic curve, to projection of gamma which is gamma 2, it is a tangent for that. Conclusions: if J of 0 S naught is 0, that means that determinant is 0 at one point, then the datum curve has a characteristic direction at that point. What does that mean? Datum curve has characteristic direction at S naught. What is characteristic direction at S naught? A P naught, B P naught, C P naught, because P naught is the point, F S naught, G S naught, H S naught. And what is the saying that datum curve has a characteristic direction? Its tangent, which is F prime S naught, G prime S naught, H prime S naught, that triple is proportional to ABC. And if it is 0, J0S is 0 for every S in a subinterval I dash, then gamma dash is a characteristic curve for the quasi-linear equation. Proof of 1. So, J0 S naught is given to be 0, right, and we want to show that datum curve has a characteristic direction at that point P naught. So, J0 S naught is 0 if and only if this is just expansion of that determinant. AB one column, F prime G prime in the other column, that determinant is precisely the left hand side, that is equal to 0. Since U is a solution to quasi-linear equation and Hs equal to U of FSGS holds, we know this. We have, let us compute this, Cp naught G prime minus Bp naught H prime. What is Cp naught? From the equation Aux plus Buy equal to C. Therefore, that Cp naught is equal to this quantity in the brackets, Aux plus Bui. At the respective points A and B are AB and Ux Ui are evaluated into G prime S naught minus Bp naught into H prime S naught. How do I get H prime S naught? From here, differentiate this with respect to S, take S equal to S naught, that will give you this by chain rule, Ux F prime plus Ui G prime. Now that is equal to, after simplification, is this, but here you observe this thing in the bracket is precisely the left hand side with a minus sign. So that is 0, therefore this is 0. So this proves 1. So one is we have proved on the last slide that gamma has a characteristic direction at the point P0. Proof of 2. From 1 we conclude that gamma dash is a characteristic curve if J0S equal to 0 for all S in I prime. What is the part 1 says? Whenever J0S equal to 0 and you have a solution, then that has to be characteristic curve, the datum curve has characteristic direction at that point, but in this case it happens for S in I dash, therefore gamma dash is a characteristic curve. That is the definition of a characteristic curve. If J0S equal to 0 for all S, then by lemma gamma itself is a characteristic curve. So when such a thing happens, the Cauchy problem is called characteristic Cauchy problem. The Cauchy problem where the datum curve is a characteristic curve, that is called a characteristic Cauchy problem. Now we have lemma 2, this is what is the result, which says what happens when transversality conditions, what is to be expected of solutions on how many in number. So consider the Cauchy problem for QL such that for every S J is 0. Okay. Conclusions: take a point in gamma. If gamma is a characteristic curve, okay, then there exists infinite number of integral surfaces, infinite number, which contain a part of the datum curve gamma containing the point P0. That is always there, right, local solution we have been talking about. So, this will always be there, but here the interesting thing is infinite number of integral surfaces if gamma is a characteristic curve. The earlier lemma one said if you have a solution, then curve gamma must be characteristic curve if this j is identically equal to 0. Now, this is opposite, kind of converse. If j is 0 throughout and gamma is a characteristic curve, then not only there is a solution, but actually infinite number of solutions exists. And if gamma does not have a characteristic direction at any of its points, then no solution. Cauchy problem does not admit a solution. Note, in this theorem we are assuming that j is 0 throughout for all s in I. So, how do we show infinitely many solutions exist? What we do is this, let V denote V1, V2, V3 denote the tangential direction to gamma at the point P0. So, imagine this is your gamma, this point is P0, this is the tangential direction which is okay, this one. Now, choose any direction W such that the set V1, V2 and W1, W2, this is in R2, is linearly independent in R2. We will see in a moment why this we are assuming this. Is it possible to choose? Yes, it is possible to choose, because once you know V1, V2, that is after all one vector in R2, you can find infinitely many such vectors W1, W2, so that this set is linearly independent. And W3 you can simply add to that. There is no condition on W3, the only condition is on W1, W2 and V1, V2. So, it can be done. In fact, infinitely many ways you can do this. That is the reason why we are going to get infinite many solutions. We will see that. So, choose any curve gamma tilde in omega 3, that is we had a gamma, we had a point P0 where we had some tangential direction. Now, what we are asking is choose anybody else, tangent has to be different, something like that. This is another curve, in fact it can be a curve, it can be a straight line as well, we are going to see that. Suppose a curve you take, no problem. So, this is gamma tilde, take any curve gamma tilde in omega 3 through the same point P0 such that the tangent to gamma dash at P0 is in the direction of W. That one easy way of ensuring that is to take straight line. So, you have gamma here, this is the point P0. So, you take some curve, no, I do not want to take curve. So, you had a gamma, you had a point P0 and here through P0 you fix a direction W and you take a line, that is it. A line passing through P0 with direction W, that is simply given by P0 plus some parameter alpha times W. Okay, this is the vector form of the line, right. So, of course, the tangent will be the direction W. So, as a consequence j gamma tilde P0 will be non-zero, because on one hand you had f prime g prime, right, earlier, and here you had that AB, because of that you got things 0. Now, you have taken somebody who is so this was 0 earlier, that means f prime g prime is proportional to AB. Now, I replace this with a new thing W1 W2, this will be non-zero. Okay, because this is not linearly independent, sorry, W1, W2, V1, V2 are linearly independent. Therefore, as a consequence W1, W2 and f prime s naught, g prime s naught, both these columns are linearly independent. So, determinant is going to be non-zero. Now, I can apply existence uniqueness theorem. So, what happened is that initially we had a curve gamma, there was some problem because j was 0, we could not apply the existence uniqueness theorem. Then we chose another curve gamma tilde, for which existence theorem can be applied, As a consequence, we get a kind of surface, okay, which contains a part of this gamma tilde, and as a consequence a part of gamma will also be there, because that is a characteristic curve. So, the surface is called S tilde, that contains a part of gamma also, because gamma is a characteristic curve. So, tangent plane at P naught to S tilde contains two vectors V and W. V is there because the curve gamma is there on the surface, and V is a tangential direction, basically it is the characteristic direction at P naught, and W is also there in the tangent plane. So, in fact, the tangent plane is given by the subspace of R3 spanned by the two vectors V and W, that is the tangent space, and tangent plane will be at the point P0, origin will be at P0. So, we have got that. So, there are infinite number of directions W having the property that V1, V2, W1, W2 is linearly independent, we already saw this. Therefore, we get an infinite number of integral surfaces such that a part of gamma lies on each of them. The part might vary from surface to surface. All of these integral surfaces are pairwise distinct because the tangent planes are having different directions. Okay, the orientation of the tangent, of course tangent plane is always a two dimensional quantity, but it will be changing. One guy who is always be there in that direction in the tangent plane is the direction of the characteristic direction, but the other direction is the W. If you, as you change W, two planes are not same. You have infinitely many solutions because you have infinitely many choices for W. So, second proof of second one, assume that there is a solution. Then by lemma 1, datum curve must be a characteristic curve, and we have assumed it does not, it is not a not only it is not a characteristic curve, it does not have a characteristic direction at any of its points. That is the hypothesis of part 2 of lemma 2. So, it contradicts. Therefore, Cauchy problem does not admit a solution. So, this completes the proof of 2. Now, we are going to illustrate these two conclusions of lemma 2 with the two examples. The first example we are going to consider is this equation xux plus yuy equal to 2u, ux0 equal to x square is the Cauchy data given for x positive. Okay, let us start solving. So, first thing is you need to parameterize the Cauchy data, which is this x equal to s, y equal to 0, z equal to square. Then we have to write down the characteristic differential equations, which is this. Now, we have to solve this with initial conditions, so that at time t equal to 0, this it passes through points of gamma. So, this is the initial conditions. Solutions are very simple, one can write this. Equations are linear equations, right, dx by dt equal to x. So, solution is constant times e power t, here also constant times e power t, here constant times e power 2t. What that constant turns out to be coming from this initial data. So, these are the solutions. Now, what is the next step that the existence uniqueness theorem told us? Using the first two equations, namely for x equal to xts and y equal to yts, express t as a function of xy and s as a function of xy, go and substitute in the third one and propose your solution. If all is well, that is going to be your solution. And here we cannot express explicitly. You can see x equal to s e power t, y equal to 0, there is no way you can solve for both s and t from this. But suddenly we see that we look at the third one, that is s square e power 2t, that is s e power t is whole square, therefore z equal to x square as solution. We have an I for a solution maybe, and tempted to declare that my solution is going to be uxy equal to x square. Okay. It solves a Cauchy problem. Of course, we can substitute and see it actually solves, but who guaranteed that this will be a solution? Because you have not done the application of the theorem, because if you want to apply the theorem, you have to check that the transversality condition is met. You have not done that. So, somehow you guessed, luckily it is working, that is it. Can you give me one more? Can you say this is the only solution? We do not know. Okay. So, this question is still to be settled. So, let us go through formally go through the theorem. To know that if a solution exists or not, we have to rely on the theorem. Look at the Jacobian, that is 0 everywhere. So, I cannot apply the theorem. So, anything can happen. Now, can we conclude something from lemma 2? Gamma is a characteristic curve, one can check. It just means one more thing you have to check. What is the tangential direction to gamma and what is the characteristic direction at this point? Both will be proportional. Please check that. Then lemma 2 asserts the existence of infinitely many solutions. Done. Let us find some of them. Yeah, theorem says infinitely many. Theorem also gives an algorithm which can be implemented. We will do that. So, take a point on gamma, say this point P. I do not really need to put S naught, so I just put S. All of us know that S is fixed in this, right. The point P naught is fixed. This is how a typical point looks on gamma S0 S square. Fix a W such that W1, W2 and 1 0. What is 1 0? It is that V1, V2. That is 1 0 in this example. That is linearly independent. Done. Now, take gamma tilde as this. This, if you see, is just a straight line passing through the point P having the direction W. P, I have used the zeta here, W. If you write in component form, this is what you get. Okay. S, P is what? S 0 S square plus zeta W1, W2, W3. So, if you expand, you will get this. So, it is a straight line passing through P having the direction W. In fact, we may take W equal to 0, 1, W3. Okay. That means, I am setting W1 equal to 0, W2 equal to 1. Why is that? Because what you want to show infinitely many solutions. Even now, suppose I show for each such W there is a solution, do we still have infinitely many? Yes, because W3 is still arbitrary, W3 is in R. One can do much more, but I am already showing infinitely many solutions. There are many more solutions also. Solution of the characteristic system of ODE satisfying these initial conditions, which are now based on gamma tilde, is given by x equal to SET, S e power t, y equal to zeta e power t, z equal to s square plus zeta W3 into e power 2t. Now, we can express t and s in terms of x and y as follows: t equal to capital T of xy equal to log x by s and zeta is equal to sy by x. Please note that s is fixed as far as gamma tilde is concerned. Substituting in the expression for z of Ts, we obtain the solution as u tilde of xy equal to x square, that is s square into e power 2t is x square plus sy by x, that is the zeta here, into W3 into e to the power 2t, which is x by s whole square, it comes from here. So, on simplification, the solution u tilde becomes x square plus W3 xy by s. Solution to the Cauchy problem with datum curve gamma tilde was obtained as this on the previous slide. U tilde of xy is x square plus W3 xy by s. Please note, this is not one solution, this is infinitely many solutions because there is a arbitrary W3 in the formula. So, with the choice of W equal to 0, 1, W3, gamma tilde takes the form, we introduce gamma tilde with respect to W1, W2, W3, but we made a choice that W will be 0, 1, W3. Therefore, gamma tilde looks like this: x equal to s, y equal to zeta, z equal to s square plus zeta W3. Zeta belongs to real numbers. Observe that u tilde of s zeta, that is substitute x equal to s and y equal to zeta, you get s square plus zeta W3. But what is s square plus zeta W3? It is this, the z coordinate. What is s and zeta? They are x and y coordinates respectively. It means that the entire gamma tilde lies on the surface S tilde. Does that surprise you? Because the applying existence and uniqueness theorems gives us only for zeta nearby 0 that gamma tilde lies on S tilde. It should not surprise because the existence and uniqueness theorem is a very general one. It is applicable for all sorts of Cauchy problems, and what we are working with here is a specific Cauchy problem. Therefore, the solution can behave better. Next question is actually, can we apply the theorem? Of course, we have solved and got this expression for u tilde of xy. Is the theorem itself applicable? Recall, our original problem is a characteristic Cauchy problem where we had this determinant, right. This S0 corresponds to A and B, and this corresponds to original f prime and g prime, and that was 0 for all s. So, it was a characteristic Cauchy problem. Then what we did is that this continues to be a 0, now we change to gamma tilde. When we change to gamma tilde, what is the corresponding f dash g dash? That is W1 W2, which is 0 1, which is equal to S, and which is not equal to 0 because we are in the region S greater than 0. So, the theorem is applicable, and that will give you, as you know, local solutions with respect to the datum curve. But however, we have obtained here by the computations, we see that we indeed have a global solution with respect to the datum curve. Observe that u tilde of x0 equal to x square also holds. What does that mean? That means that the entire gamma lies on S tilde. That means our original datum curve itself lies on S tilde. So, note all these solutions are also global with respect to domain. They are in fact defined on R2. Okay. They are defined on R2. So, there are infinitely many solutions. Now, let us look at the second example. This I think we already solved using Lagrange's method, ux plus uy equal to 1. If not, let us do again. Let us do now. So, the characteristic system of ODE is dx by z equal to dy by 1 equal to dz by 1. So, integrating this set of equations, we get this x minus z square by 2 equal to C1. The other one will give you y minus z equal to C2. Therefore, Lagrange method says f of C1 C2 equal to 0. That means take any arbitrary function f and this equal to 0. Of course, it remains that this is valid for only those x y z for which this kind of quantity, this tuple lies in the domain of f, that is always there. Second thing is that you should be able to solve for z in terms of x and y, only then I would like to call this as a solution. Okay, that is done. Now, we will substitute C1 C2. So, now I think we will find the f using the Cauchy data, that should fix the f, then we will get the solution, that is the idea. Whether we will be successful or not, we will see. So, x equal to s square, y equal to 2s, z equal to s, this quantity equal to C1, substitute for x equal to s square and z is equal to s, you get this. So, that will give you s square equal to 2C1. Now, from the other one, y minus z equal to C2, when you substitute the values for y and z, you get s equal to C2. Therefore, there is a relation between C2 and C1 that we get C2 square equal to 2C1. So, we are going to substitute for C2 whatever that y minus z and C1 this. That gives a quadratic equation for z. When solved, we get this expression y plus or minus root 4x minus y square by 2. Now, gamma 2, the projection of datum curve, lies on this curve of 4x equal to y square. Therefore, this function is not differentiable because whenever 4x minus y square is 0, there is trouble, square root function is not differentiable. So, u is not differentiable at any point of gamma 2. Therefore, Cauchy problem has no solution, whatever we have obtained. Now, using method of characteristics, we will attempt to solve the same problem again. So, we have to write the parametric form of gamma, done. Then system of characteristic ODE is this. Now, we have to solve this with initial data, this, so that at t equal to 0, the characteristic curve lies on the datum curve, done. When we solve, this is the expressions we get for x, y and z. So, to know if a solution exists, we have to rely on the existence and uniqueness theorem, because it is not obvious whether I can use the equation for x and y and get an expression for t and s. So, let me do that. Jacobian is this, it is 0. So, Jacobian is 0. Therefore, existence theorem cannot be applied. Now, what does lemma 2 ask? It asks whether it is a characteristic curve. If it is a characteristic curve, answer is infinitely many solutions. So, we check what is it a characteristic curve or not. The characteristic direction at any point on gamma is the ABC, that is S11, but tangential direction is 2S2, 1. So, both are not proportional, they are not parallel. Okay. So, therefore, gamma is not a characteristic curve. Therefore, the second part says you do not have solution. Conclusion 2 of lemma 2 says it has no solution. Okay, now let us go back to the 3 examples that we were discussing in lecture 2.1, that is this. Recall the PDE was Ux equal to Cu, in fact it is like ODE, there is no T dependence, and then Cauchy data 1, 2, 3, Cauchy data 1 had unique solution. Note where is it prescribed? It is prescribed on the t axis, while Cauchy data for 2 and 3 are prescribed on the x axis. In one case you have infinitely many solutions, in the other case there are no solutions. Then we ask this question why they behave differently. PDEs are same, and on t axis you have uniqueness, on x axis you may have many or no solutions. Then we had this question, who is special, is it t axis or x axis, and we said answers later. Now it is a time for answers. Cauchy problem 1, J0s. So, we are trying to use lemma 2 and try to answer. J0s is 1, therefore, we have existence uniqueness theorem, therefore, uniqueness is what you expect, done. It is in tune with the assertion of existence uniqueness theorem. Now, second Cauchy problem, we had J0. Now, the question is it a characteristic curve or not? So, transversality condition is not satisfied, fine. At every point on gamma, the characteristic direction is f prime g prime h prime, which is equal to 1 0 c into e power cs, and it coincides with the tangential direction. Therefore, it is a characteristic curve, therefore, there are infinitely many solutions. That is what lemma 2 also says. Cauchy problem 3, J is 0. So, we ask whether the curve gamma is a characteristic curve or not. It is not a characteristic curve. So, the conclusion 2 of lemma 2 says no solution. So, that is the thing. Here transversality condition is satisfied, so we do not go further. Here we check gamma is a characteristic curve, because ABC is this, f prime g prime h prime is this, and here gamma does not have characteristic direction anywhere, therefore no solutions. This is a characteristic Cauchy problem, we have infinitely many solutions. The transversality condition is not satisfied for both Cauchy problems 2 and 3. Datum curve turned out to be a characteristic curve in the case of Cauchy problem 2, that is why we had infinitely many solutions. Datum curve is not a characteristic curve for the Cauchy problem 3, therefore no solution. Now let us answer the other part. Which axis is special, t or x, and why? Special things have to be handled carefully. So, you answer for yourself this question, because the answer lies in special things have to be handled carefully. Something is not special, does not matter, you give anything you want, no, there is no problem. So, existence uniqueness theorem asserted existence of a unique solution for Cauchy problem if transversality condition is satisfied. Denote the corresponding Jacobian as J0 S naught. If this is non-zero, then it will be non-zero for S belonging to an interval containing S naught, for the reasons that things are involved in the determinant are continuous functions of S, and determinant itself is a continuous function. So, given the local nature of the assertions in existence and uniqueness theorem, the following cases exhaust all the possibilities in when the transversality condition fails at S naught. J vanishes at all points of of some interval containing S naught. Nearby S naught is what we are worried about. On some interval J is 0, or it does not vanish at any point of some interval containing S naught except at S naught. That is an isolated point in some interval. In rest of the points of the interval J is not vanishing, but only at S naught it vanishes, or it can happen like this kind of limit point. You find a sequence of Sn such that J is 0 at the point J0 Sn and Sn goes to S naught, otherwise it is not 0. Okay, imagine a function like x sin 1 by x, 0 is the limit point of zeros of this function, something like that. Now, lemma 2 answered the cases 1 and when the case 1 happens, when J is identically equal to 0 on some interval containing S0, and theory seems to be elusive when situation 2 or 3 occurs. One has to look from case to case and make conjectures, and I do not think there is any complete theory available written in a textbook. So, let us summarize. We have learned how to solve a Cauchy problem using method of characteristics. We have understood what may happen if transversality condition is not satisfied, and in the next lecture we solve some more problems from first order partial differential equations up to quasi-linear equations, and then we will move on to general nonlinear equations or general equations later on. Thank you.